in statistics. That's right, we always have a good time in statistics class. So let's start our second chapter here. We're going to be talking about three different things. The first two things are going to go by pretty quick, and we're going to focus primarily on these things called z-scores. Number one, percentiles. You might have heard, getting back some standardized tests, maybe your ACT or some other type of state testing. They may have said, oh, your math score, you were in the, 98th percentile. That sounds good. What does that mean exactly? What does that 98 really means? So we're going to first discuss that on what it means to be in a certain percentile. So one way to describe the location of a value in a distribution is to tell what percent of observations are below it. Now, I know it's kind of ironic I put the word below the line that below needs to go in. I just couldn't make it so small, and then you guys are like, what does that say? I can't see. So I just ironically, no pun intended, put below the line you need to put it in. So the pth percentile, where p can be any number between 0 and 100, of a distribution is the value with p% of the observations less than it. That is the key word out of all of this, less than it. So on her first AP Stats exam, Jenny scored an 86%. What percentile, flip-flop, is she in with respect to the rest of her class? Okay, so if here's a split stem plot, if you will, here's her 86 right there. Now, if we're talking about the percent of individuals that fall below her, well, let's see how many scores there really were below her. So there was an 85, so there's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 21 scores below Jenny. Okay, she had 21 scores below her. Out of, well, how many people are in this class? Well, if there's 21 below her, she's 22, 23, 24, 25 people. 25 scores overall. Now, we just need to talk what that is as a percent. So 21 out of 25 is 84%, or we would call her in the 84th percentile. Okay, her 86% on her test puts her at the 84th percentile when compared to the rest of her peers. So in the context here, exactly what I just said. Okay, now what gets a little confusing is you're going to have numbers that represent percents, and then we're going to talk about what those percents are as percentiles. And people might get a little confused that those two numbers, the percent and the percentile, are potentially, or most of the time, two different numbers here. All right. But just know that the 86% is what she got individually when she's not going up against anybody else. But in terms of the whole class, she's at the 84th percentile. She's better than 84% of people in her class, which means 16% of people did better than her. So for example, if you're in the 98th percentile for some test, that means you did better than 98% of everyone else that took that test. And only 2% of people did better than you. Next up, these things called ogives. They look like ogives. They're called ogives. So a histogram does a good job of displaying the distribution of values of a variable, but it does not tell us about the relative standing of an individual observation. Again, what I mean by relative standing of an individual observation are percentiles. Okay. If we want this information, we will need to construct what's called a relative cumulative frequency histogram, aka an ogive. Now, you can certainly call this a relative cumulative frequency histogram. I prefer just to call it an ogive. Okay. Here's the good news about ogives. You will not have to create them on your own. The only thing you will be required to do with an ogive is be able to interpret it. I will give you the graph. I will ask you some questions like maybe these 1 through 5s, and you simply have to read the graph to answer the question. Those are the types of questions you will see on the test and in the homework. So here's how an ogive works, all right? We're still using our class data that we had back here from the first AP Stats exam, okay? From the 67 all the way up to the 93%. So count is basically how many. We could say count or we could say frequency. Same thing. So how many people got between a 65 and 69? One person. So we're going to put a 1 there. Get a little bit thinner of a lead here. There we go. How many people got between a 70 and a 74? 1, 2, 3, 4. And so here's where my split stem plot really comes in handy. Oh, wrong way. Oh, too far. There we go. Had 4 people. 75 through 79. Well, there's 1, 2, 3, 4, 5, 6, 7 people. Between 80 and 84. 1, 2, 3, 4, 5, 6, 7, 8 people. Between 85 and 89. 1, 2, 3. That's including Jenny's. And between a 90 and 94, 2 people. Now, a cumulative frequency is basically as we go through this list, we're going to be accumulating our frequencies here, our counts, okay? So as we start off here, we just have our one person, okay? There's nobody that came before this person. This is the minimum value. Now, for the next part, we have these 4 people, but we're accumulating as we go along. So we're going to take this 1 and add to it, if you will, the 4. So at this point, when we have gotten up to a score of 74, there are 5 people that have gotten a 74 or lower. Okay, so we're going to keep accumulating, if you will. Oh, that's way too big of an eraser. Come on. Okay. Well, I wanted to erase that. There we go. All right, so now we're at 5 people. We're going to add 7 more. That means we'll have 12 total along the way. 12, add 8 more. Now we have 20 people. 20, we're going to add 3 more. We're at 23. And 23 and add the final 2. And there's our total of 25 people that we had mentioned earlier. Now, a relative cumulative frequency. Well, cumulative frequency uses these numbers, but a relative, anytime you see the term relative here, we're talking percentages. So at this point, we now need to convert all of these numbers, 1, 5, 12, 20, 23, and 25, into the appropriate percentage. Now, all of these numbers are out of 25. Now, here's the nice thing always about the last entry here. Since at this point you've accumulated everybody, the last thing's always going to be 100%. That'd be 25 out of 25. So again, you can kind of think of this as 25 out of 25 makes our 100%. 23 out of 25 makes, 92%. 20 out of 25, that's 80%. 12 out of 25 makes 48%. 5 out of 25 represents 20%. And 1 out of 25 represents 4%. It's these numbers here that we're going to use to create the ogive. And again, you don't have to create it, but this is how it is created. You need these relative cumulative frequency numbers that they keep continually increasing until you have got all 100% of your data set. So then that's what I did. From 65, at 65, I didn't have any people below that. So that's why this is at 0. When I get to 70, I've gotten that one person. That's it. And that one person represents 4%. So here's 5%. I kind of approximated. This is really a little bit below the 5%. And so I connect. My next percent's at 20. So by the time I've gotten to 74, I've covered 20% of my people. So 20%, slide it over, go up to there. And then up to 48%, which this isn't looking legit. Where did I mess up? Did I mess up somewhere? It says Ogive whack. What's going on? Times 4, times 4. No, that's good, that's good. I feel like I did something wrong somewhere. I don't know. Maybe my Ogive's just screwed up here. Maybe it's just screwed up. Hopefully it's screwed up. I don't know. Maybe you guys can point out to me if I did something wrong here. I can't think. All right. So anyway, these should match up with these here. So here's how we're now going to read an ogive. What grade is the center of this distribution? Well, the center, if you think about it, we can talk about mean or median. Median is going to be ideal because the median is at the 50th percentile. And all of these percentages here kind of represent percentiles. So if the median's at the 50th percentile, here's the 50th, we just need to shoot over from the 50th percentile, right? Oh, but not in white. That's why I can't see it. Oh, still not in white. Come on. Shoot over, and boom, wherever that hits, now we're going to drop straight down. So the center of the distribution, we have to approximate this. What do you guys think? 78, 79%? Let's go 78. We'll say the median is at 78% using our ogive. What grade corresponds to Q1? Well, Q1 is the 25th percentile. So now we just need to do the same thing, except instead of 50%, we need to go down to 25%. We need to shoot over. Let's just make our line longer. And make that shorter. There we go. So we can see it is approximately, what, almost 75, I'll say 76% is Q1. What grade corresponds to the 60th percentile? Same thing, go up to 60. Where are we at in terms of 60? Go to there, come to here, come down. We are at approximately, what, 81, 82? We'll say 81. 81%. What approximate percentile would a 77% put you in? So I'm not asking about a percentile. I'm saying if I got a 77%, well, now we're going to use our ogive the exact opposite way we've been doing it. I need to find 77, which is maybe right around there, we'll say. So first I start with my vertical line, go up to my ogive, and then go horizontally over to see where approximately that is. And look, I'm right in between the 35th and 40th percentile. So I might estimate and say I would be at the 37th percentile with a score of 77. Not too great, you know. I've done better than 37% of people in my class, but that still means 63% of people did better than me. And then number 5, what minimum score is required to be in at least the 90th percentile? Well, the 90th percentile would be right there. We'll just butt it up right there. And now let's drop straight down to our scores. So it says, what is the minimum score? Well, this looks like it's at, what, maybe 88? So I would need to get at least an 88% on my test to be considered at least in the 90th percentile. So an 88% or more, I'm going to be in the 90th up to 100th percentile. Okay? Now, one thing about percentiles, before we get away from this, you can never technically be in the 100th percentile. Because if you think about that, that means you did better than everybody, including yourself, because you are one of the people. You know, if there are 100 people taking this test and you outbeat everybody, technically you did better than 99 out of 100 people. You didn't beat yourself. So really, kind of the maximum, if you will, that really makes sense is the 99th percentile. You can get to, you know, the 99.9th percentile if 1,000 people took the test and you have the top score. So for those in calculus, it's kind of like a limit. You're approaching 100%, but you can never truly get there because you can never do better than yourself. Now, standardizing. This is where we get into that whole z-score thing. So we're going to stick with Jenny's 86 on her first test, and let's say she takes a second test and she still gets an 86%. Sweet, she's consistent. Compared to her first score, she stayed the same, obviously, right? 86, 86. But how does she compare with her peers the second time around? Now we're going to compare percentiles, okay? So here we said she was at the 84th percentile. 84th percentile. Now over here, let's figure out real quick what her percentile was. So here's her 86. So she did better than 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 of her peers. And I'm assuming there's still 25 people in this class. I don't think anybody dropped between the first and second chapter test, but who knows. Notice now, compared to the rest of her peers, she's not doing so hot, right? Like there was an increase of 40% more people did better than her between the chapter 1 test and the chapter 2 test. Now, thankfully, she's not graded against everybody else's grades, okay? She still is averaging an 86%, and she's graded purely on her performance, not the class performance. But if she wanted to kind of compare herself to everyone else, she kind of did worse. You know, more people piggybacked over her and got a better grade on the second test compared to the first test. So we could compare the percentiles like we just did to see which test Jenny really did better on at compared to her peers. She did better on the first test compared to her peers than the second test. But what if we didn't have all of the data? What if we didn't have all of these numbers? Then we wouldn't be able to compute the percentile. I mean, realistically, are you going to know what everybody else got on their test? No, not everybody's going to tell you. Probably these people here are going to feel maybe a little bit embarrassed or ashamed that they scored that low. They're either going to lie to you what their test grade was, and then you have an incorrect percentile that you've calculated, or they're just not going to tell you at all. So realistically, we don't have all the data. So what can we do? What statistical values do you think we would need in order to determine Jenny's performance? Well, here's where we start getting into our socks again. Okay, I put 4 lines out here because it's more than what we really need. Ideally, the main things we need to know about our entire distribution, what's really going to help is if we know what the mean score is, and oftentimes if you ask your teacher like, hey, what was the mean score on the test? That's something that your teacher would, easily tell you more so than everybody's exact scores. Now, besides the mean, you really should know how spread out the data was, right? So you might ask for, and since we're talking about mean, what's the standard deviation? Because those two things, again, go together like peanut butter and jelly. Because it's peanut butter jelly time, peanut butter jelly time, way yeah, way yeah. Sorry, I was getting back into my high school days. So these 2 lines over here, we don't really need anything. We need to know mean and standard deviation. So we can use Jenny's score of 86, and if we knew the mean and standard deviation, we can get her approximately how well she did compared to the rest of her class. So to get a z-score, or what's called to standardize a value, we need to take 2 ways we're going to write this. I'll write it out first in words here. So we'll say, how are we going to call this? Actual value, like your value, basically Jenny's value, minus the mean. We're going to figure out what's the difference between your score and the mean, and we're going to divide it by the standard deviation. All right. So what that is going to kind of look like symbolically here is your value is X. Okay. The mean, and we could use X bar, but we're going to start using more population-wise stuff here. So we have this Greek letter mu. Kind of looks like a U that has a tail curling out front. And a lot of people that I've had in the past think that I'm really doing like a fancy looking M here. But think of it this way. Think of it as a U, and then you're putting a curl out in front of it. So it's called a mu. Okay? It's not really an M, it's really a U with a tail coming out front. Standard deviation on your calculator was that SX, but in terms of population, it's going to be a lowercase sigma. Okay, it looks like an O, and then you give it some like, hey, look at my cool hairdo here. Something like that. All right. So this just means mean and standard deviation. If you wanted to really put X bar and SX, that's fine. I don't really care at this point. So compute and compare Jenny's z-scores for her 2 tests. So a standardized value is often called a z-score. A z-score tells us how many standard deviations the original observation falls away from the mean and in what direction. So we'll talk about specifically how do we know which direction we're going, if we're below or above. All right. So if we're talking about the first test, we know Jenny scored an 86%. Okay. And I'm just going to say 86. I'm going to leave out the whole percent concept. All right. Now, the other things I need to know are what are the mean and standard deviation for the first test? Well, I didn't really have those numbers. Okay. So I'm going to go ahead and kind of set this up, and then I'm going to pause the video and go grab the mean and standard deviation for the 2 tests. Okay. I'm not actually going to do it in real time here and waste all of your times. So let me pause. I'll be right back. To be right back is just going to be like 2 seconds. So hold on. And I'm back. Okay, here's our information now for test 1 and test 2. The mean on the first test was an 80. The standard deviation was approximately, I had to round this, 6.1 to 1 decimal place. Now, in the calculator, I still use that S sub x. You'll notice below the SX, there's a sigma sub x. I never will use that part of the calculator. You always use the SX. For the second test, I had a mean of 83.8 and a standard deviation of 9.3. So now, let's compute our z-scores. So the z-score on her first test, she scored an 86. We're going to subtract away the mean. She was, 6 points away from the mean. But with the standard deviation, which is a measure of spread, each standard deviation is 6.1 percentage points, okay? So she's 6 over 6.1, and we're going to round this here. We're going to be basically almost at 1. So 6 divided by 6.1 is approximately 0.984, okay? Now, what this is saying is that she is 0.984 standard deviations above the mean. I mean, we know her 86 is above the mean of 80, okay? Now, we'll talk about how we know it's above versus below, just given the z-score. If I was just given this number, I could tell you if she did better or worse than the mean. So this is her z-score for the first test. She's about 1 standard deviation above the mean. All right, for test number 2, her z-score, 86 minus 83.8 over 9.3. So 86 minus 83.8, we're looking at what? Just 2.2 over 9.3, and that is approximately 0.237 standard deviations, and this is still above the mean. The reason why I know I'm above the mean is because I get a positive z-score. Okay, think about this. If this number was smaller than 83.8, I'm going to end up with a negative value. And because it's negative just means is I didn't do as well as the mean. I'm under the mean. So if your z-score is positive, if z is positive, that means you're above the mean. If you get a z-score that's negative, that just means you are worse than the mean. Okay, so it is possible to get a positive or a negative z-score. It just lets you know your relative position with respect to the mean. So again, you could use these to compare Jenny's performance if you didn't have all the data. You can say, hey, she was 1 standard deviation above the mean versus she was only 0.237 standard deviations above the mean. Since this score is farther away from the mean, the better she did. Okay? So compute and interpret Maxwell's score of a 75% on the first test. Well, the first test I said was a mean of 80, and the standard deviation was approximately, what did I say, 6.1. So Maxwell, if I said z sub max, he scored a 75 minus 80 divided by 6.1. That's going to put him at negative 0.82, basically. So again, the negative here just means he did worse than the mean. He was under the mean, so we got a negative score. So he is close to being 1 standard deviation below the mean. All right. And compute and interpret Brittany's score of a 95 on the second test. We said the mean of the second test was an 83.8, and the standard deviation was approximately, I don't remember, what was it, 9.3. So Z sub Brit, we've got a 95 minus 83.8 divided by 9.3. So 95 minus 83.8, that in parentheses in my calculator, divided by 9.3, puts me at a z-score of 1.204, if I wanted to go that far, I mean. So she is 1.2 standard deviations above the mean. All right, so she is doing pretty well with her 95%. Now, the last problem and I want you to do this on your own. Finish the video out with this. I will check this tomorrow in class for credit, and we will go over it together. So who did better? Jeff, who scored a 79 on that first test. Go ahead and still use the same mean and standard deviation we had been using. Or James, who scored an 82% on the second test. Now, at first glance, you might go, well, 82% is better than a 79. True, but we're going to be talking about with respect to everyone else in class. Okay, so you can do it one of two ways. You can do percentiles or you can do z-scores. Z-scores require less work because you only need two other numbers, mean and standard deviation. Percentiles mean you need to know all of the data, which you do know, so you have a couple options there, and we will discuss them. All right, that is all for the first video. Good luck and adios.